So good morning everyone. Today we are going to study of a topic from optional paper 2, that is mechanics, and in that we'll study moment of inertia. Generally people consider this as one of the most difficult subject. These are the most difficult subject in UPSC Maths Optional, that are modern algebra, fluid dynamics, mechanics, dynamics, statics. Okay, since people don't have not studied this in their graduation, if they have done graduation with mathematics, so it is not a pure mathematical part, it is basically inclined towards physics. Okay, so but I find it mechanics portion to be very scoring, and I will not say easy, but if you once you grasp the concept, then it is solvable. And also the thing is, solving these questions in examination gives you extra edge. Normally all the people there, serious candidate I would say, are able to solve questions from linear algebra, linear algebra, vector space and LPP, PD, OD, but these gives you extra edge there. Okay, so now moving ahead, some basic definition. You are I think that you are already aware with these definition, but a quick recap. Okay, so you have studied this in class 12th also, this moment of inertia, but here we studied product of inertia and momental ellipsoid. So level is up, but initially we'll start with the basics only. I consider any student who have done 12th in this 12th with science stream would be able to understand this chapter. You don't need graduation in mathematics or any subject, say engineering, to understand this. Okay, so moving ahead, the first definition which we have here is about rigid body. So a rigid body is a body, I would say, such that the distance between two particles in that body is invariable. That is invariable. It doesn't changes. Okay, or for our study in future, if a force is applied to that body, we won't consider that the body would change its shape. It would move up and down. It could have a motion it could have a circular motion, rotational motion. But if a force is applied, the shape of the body doesn't changes. The rigid body has invariable size and shape doesn't change, and distance between any two particles remains always same. Okay, so distance between any two particles in this, as I told you, any two particle is always same. So if this clearly, if the distance is same, okay, so you don't have to learn about the shape and the size, that won't change. If the distance would change only between two particles, then only the shape would change. So that's the definition of rigid body. Okay, so our concept here of a moment of inertia of a particle. Okay, so why? See, moment of inertia is used in understanding the rotational motion. Okay, mass is used for understanding the linear motion, but for that we need, for rotational motion, we need to study moment of inertia. And one thing you must notice is that moment of inertia depend upon the axis we have chosen. Okay, so we'll study this. That consider from a mathematical point of view. See, you have to learn how to calculate moment of inertia, formulas, difficult formulas. We don't have to go to the physics portion. Okay, that what happens, why we use moment, that is not our concern here. As a mathematicians, we only need to know how to calculate moment of inertia of complex bodies or in 3D bodies like conicoid, these difficult ones. Okay, so consider we'll go straightly to the mathematics part. Okay, so consider a mass of m and a line AB. This is line AB, suppose. Okay, so the moment of inertia of the particle of mass m about the line AB. So I told you that moment of inertia needs an axis. See, mass is constant with respect to any axis, but moment of inertia would be changing with respect to axis, change in the axis. Okay, so it is defined as mr square. Okay, if this is the perpendicular distance here, this is the perpendicular distance of mass m from a line AB. Okay, so mr square is the moment of inertia. Okay, so this is clearly simple, and you know in your class 12th also you've studied this. Okay, so moment of inertia of a system of a particle, if suppose there are many particles, say I would draw like this, I would say there in the space there are many particles, okay, say m1, m2, this is mp, okay, and there are the coordinates which they have, the distance with respect to a line which are say r1 perpendicular to r2, rp, okay. So if the distance m1, m2, m3 have distance r1, r2, r3 from an axis, any axis, then the moment of inertia is summation of these individual particles. The moment of inertia, the system of the particle, is summation. I is equal to summation m rp square mp rp from r equal to 1 to n, say if there are n particles, okay, mp rp from, sorry, p not r, p equal to from 1 to n and mp rp square, okay. So this is how we calculate a moment of inertia of a system. If suppose if there are two bodies m1, suppose there are two bodies, two particles m1 and m2 and a line such that the perpendicular distance is r1 and r2, then the moment of inertia of this system of particle would be I is equal to m1 r1 square plus m2 r2 square. And if you write in a generalized formula, then this would be the case, okay. It depends upon the number of particles, okay. So moving ahead, now suppose moment of inertia of continuous distribution of mass, that would be say any body, be it a sphere or as a random a whole body, okay. So what do we do here? We use the method of integration. We know that we divide this into smaller particles, okay, we divide this into a smaller particle, okay, and from an axis, suppose a particle has a distance r, then the moment of inertia would be I is equal to integration r square dm. This r could be constant for each particle, or r would vary for m, okay. So in any case, this is the case for continuous body. You know, see what we have done, we have taken small element here whose mass is dm, okay, and suppose that this small particle has a distance r from this axis, then the moment of inertia for whole would be r square dm. Here r would be function of m, okay. Function of m means that r depends on the m, okay. So this is how we calculate moments of inertia of a continuous body. I think you are familiar with this idea. This is a basic understanding from intermediate level, okay. So now we understand the radius of gyration, okay. Radius of gyration is nothing, okay, case called radius of gyration. Suppose you get, it is nothing but I upon m, k square. Suppose k square is the radius of gyration, then it is equal to I upon m, where I is the moment of inertia, MOI, and m is the mass of the body, of continuous mass, anything, okay. But now when it is in continuous distribution, I told you what would be I would be integration r square dm, and what would be the mass? It would be integration dm, okay. So this is moment of inertia, okay. Now we will touch a concept which you haven't studied in your intermediate level, that is the product of inertia, okay. In the case where we take the distance along a axis, say x axis, so we take only the x coordinate, okay. Suppose this is the mass, this is a particle, I will take particle, this is a particle, so about if, and its coordinates are x1 y1 and this mass m1, okay. So moment of inertia about x axis would be what would be moment of inertia? It would be m1 y1 square, and for y axis it would be m1. Okay, so it has a square here. Okay, but in the case of product of inertia, we have, suppose if x1 y1 x2 y2 xv will be the respective coordinate of particle of masses m1 m2 mp referred to two mutually perpendicular lines ox and oy. Okay, it says that I'll do it on the next page. It says that suppose this is xy plane and there are m1 m2 m3 m4, okay, these particles with the coordinate system, coordinate x1 y1 x2 y2 x3 y3 and x4 y4, then the product of inertia of a single element, suppose that there are no more element, only m1 is there, that would be product of inertia would be p would be m1 x1 y1. Okay, and in the case where are more than one particle, what do? We add. Similarly, like case of moment of inertia, we also add in the product of inertia, that would be m1 x1 y1 plus m2 x2 y2 plus m3 x3 y3. Okay, dot mp xp. Suppose there are n element x and y here, or this could be in a sigma notation, it could be written as mi xi yi, okay, and where I is from 1 to n. This could be product of inertia. Okay, and for continuous body you can understand it would be integration of that. Okay, so what do we do next? Okay, we first try to learn to calculate moment of inertia of some simple bodies, so that we have a clear understanding about that. Okay, so first we consider a rod of length say 2a and mass m. Okay, so first we consider the axis to pass from any corner. Suppose the axis passes through this corner A. Okay, and suppose this is the rod. Okay, I'm making this so that you have a clear understanding. This is a rod, say. Okay, so what do we do here? We have to calculate moment of inertia about a line passing through one of its edges. Okay, so what do we do? Since it is a continuous body, always for a continuous body, first find the density there. Okay, so in this case the density would be rho would be m upon 2a. It is in one dimension. I have made this thicker one. Don't consider it as a cuboid. It is a rod. I have just made it to make you understand this concept. Okay, this is a rod. Okay, so don't consider it is a thin rod. Don't consider it as a cuboid. I'll do it for you. I don't want any confusion on my part. Okay, suppose this is the rod and this is A, this is B, and we have to find the moment of inertia about any axis passing through any of the corner. Okay, so suppose we consider a small length dx at a distance x. Suppose we take a small length dx. Okay, so and the mass of this length would be rho into dx, where rho is the moment of inertia, say dm. Okay, moment of inertia, rho would be density. Okay, so rho in dm is equal to density into this length. linear density, this is linear density. Okay, so moment of inertia, what would be moment of inertia? Di would be the distance from the axis, that is the x square, and the mass, that is the dm. Okay, so what do we have with di? We have rho x square dx. Okay, now for calculating the moment of inertia of the whole rod, what do we have to do? We have to integrate this from this end to this end. Okay, and since we have taken this as the origin, or I would say reference line, or the axis, the integration would be from 0 to 2a, 0 to 2a. So what would be? We get I is equal to integration rho x square dx 0 to 2a. Okay, now you can easily solve it. Now one more concept which I want to share right now only. Suppose this rho here wouldn't have been linear or continuous. See, this is m upon 2a. Suppose the rho would be given by lambda x, where x is from the distance. That is, the density of this increases with the distance. Lambda be the constant. The density increases linearly or proportional to the distance from this axis. Or it could be quadratic, or it could be any function, lambda log x. Okay, so in that case you put it that way. Okay, but for now, what do we do here? We integrate it, we get rho into 4a cube upon 3. Now here rho is m upon, sorry, this is cube, this would be 4 not, this is 8. This would be 8a cube upon 3, or this m upon 2a into 8a cube upon 3. Okay, so we get the moment of inertia as this is m 4 upon 3a square. Okay, so moment of inertia would be 4 by 3 ma square. Okay, see, we have done it. I have given you the chart, but for now okay. So about a line perpendicular to rod through an end, we have 4 by 3 ma square. Now what if for uniform length of mass about an axis perpendicular to the rod? Okay, so perpendicular to the rod, in that case, suppose this is the rod. Okay, so we have to take from the center, sorry. Suppose this is the rod, and if we have taken axis from the center O, okay, excuse my drawing skills, I'm not good at it. Okay, so suppose we consider an element dx similarly from distance x from here. Okay, so what would be the moment of inertia? This would be rho. Okay, rho into dx would be the mass, and the x square would be the distance. Okay, but this would be di, and I would be integration rho dx into x square. Now what changes here is the integrating limit. With this reference as origin, you have to take, this varies from minus a to plus a. This is of length 2a passing from center. This would be the say origin. Then you have to calculate it from minus a to 2a. In the case where we have taken from the side, or axis passing through any of the side, we have taken from 0 to 2a. But in this case, we take it from minus a to a, and you solve it, so you will get 1 by 3 ma square. Okay, 1 by 3 ma square. Okay, so now moving ahead, a bit ahead, what do we see? We calculate the moment of inertia of a rectangle. Now we have taken a 2-dimension body. Okay, so what do we do here? Suppose this is a rectangle and this passes to center. This is OY, this is OX. Okay, and suppose this is 2B and this is 2A. Now one thing, for examination point of view, this thing comes with experience. Please note that the length is given in 2A or L or A only. In this case, I am taking the case where I have taken the length to be 2B. Okay, I have taken ABCD, AB to be 2A and AD to be 2B. Okay, one thing you should note that in the examination, if you are told to calculate this, please make sure that you have the exact what I say, if this is 2A or if this is A. Okay, suppose in this case, if the length would have been A, okay, this whole length would have been A, then we have to integrate it from minus A by 2 to plus A by 2. Okay, or we have to replace A by 2. Okay, so suppose this is the whole picture here, 280. First of all, what I told you, moving ahead step by step in mathematics, what I've learned over the years, that understanding mathematics is going step by step. You should know each step, and if you go step by step, then it is easy, and if you go in a haphazard way, then you find it very difficult. First of all, you calculate the density. This time it would be surface density, mass upon area. And what is the area? Area would be 4AB. Okay, 4AB. Suppose I divide this whole rectangle into small rods, or I would say a small, these rods, infinite rods. Suppose if I have taken these infinite rods. Okay, so what would be the length of this rod? This portion, this vertical length would be 2B, and the horizontal would be, suppose this is of thickness dx only, a small. See, I have to break this into infinite such that dx tends to 0. Then only we can use the integration. We have to divide this sheet into small rods such that so small that this length tends to 0. So it is so small, dx limit dx tends to 0, or the number of length, if I divide into n, okay, then n tends to infinity. That's the basic of integration. Okay, so what do we do here? So moment of inertia, we have to calculate the moment of inertia about the axis, suppose say OX. Okay, first we calculate moment of inertia about OX. Okay, so first of all, what would be the mass of this small rod? Mass would be nothing but m upon 4ab, I would say surface density rho into area of this area would be 2b into delta x or dx, 2b dx. Right. And the moment of inertia of this small length would be about OX would be, see, this is passing through from the center, and earlier I have proved that if a rod passing to center, the moment of inertia is 1/3 ma square. Okay, this is the mass dm. Okay, so what would be the moment of inertia di? This would be rho into 2b delta x, and passing from the center, and the size of the rod is 2b, so this would be ma square upon 3, so mb square upon 3. Okay. OX will be at a distance x. Suppose this is at a distance x. If you have taken a sheet such that the length would be 2b and this would be dx. Okay, so what would the mass here would be rho into db, 2b into dx. Okay, and what would be the moment of inertia? The mass into b square upon 3. Since in the earlier case I have shown you that the moment of inertia of a small rod from the axis passing to center is ma square upon 3. So in this case I have taken the mass, and this is of length 2b, it will be mb square upon 3. Okay, so integrating, okay, this would be 2b cube. I take the constant term outside, it will be rho 2 3, and this would be b cube, and integration dx, and x, the limit of x would be, since this is the origin, minus a to plus a, minus a to plus a, minus a to, this would be 2 by 3 rho. For rho we write m upon 4ab, we write b cube. Okay, and for dx we write, the integrating we get 2a. If integrated, it is an even function, and in the case of even function it is 2 times 0 2a dx. You can easily calculate it. Okay, so this 2, this 4ab, this a, it cancel out and it forms mb square upon 3, mb square upon 3 about OX. About the line OX is mb square 3. It is saying about a line to the center parallel to the side 2a. See, it is parallel to the side 2a, then we get mb square by 3. So similarly, what would be MOY? Similarly, by symmetry, you can understand that this OY is parallel to this length, which is the 2b. So we will get MA square upon 3. MA square upon 3. So for this would be I from IOY, right? IOY, and this is IOX. Okay, MA square upon MA square by 3. See, this is very simple, and moving ahead things would get a bit tricky, but overall if you do it by concept, that is an easy concept, mechanics. Okay, so now another case, if I take suppose x and this is y, okay, and this is 2b, a, b, c, d, and this is 2a. Okay, so suppose I need to find the moment of inertia of this rectangle from an axis perpendicular to this. See, if I told you that this is rectangle and I want now the x, suppose we have calculated from this axis, I want in the 3D dimension, I want it in the z axis. Okay, in case of this z axis, what would be the moment of inertia? Okay, so in the 12th class you have studied this as a principle of perpendicular axis theorem. In this also you will study. Okay, so that is, we have to add those moment of inertia, but I will calculate it using the basic initial definition of moment of inertia. Okay, so suppose a small particle here, I would say a rectangular particle here, this will be of this length has dx and breadth has dy. Okay, so first of all, what do we calculate? I told you, first of all we calculate rho, in this case same 4ab. Okay, then we calculate the mass of the small particle which we have taken, that would be dm is equal to rho times dx dy, rho times dx dy. Now the distance from this axis, since this is perpendicular, the distance would be this distance. And what is this distance? This is x square plus y square. This is base square plus perpendicular square is the hypotenuse square. So di would be integration rho dx dy x square plus y square. It would be double integration where x would be varying from minus a to a and y would be varying from minus b to b. Okay, so calculating it, this would be I, we have been using the integration sign. Okay, so rho is the constant here, say dy, and for dx, suppose if I integrate it first for x, so it will be x cube upon 3 plus y square x from minus a to a. Okay, this will give me, I'll solve it here. Okay, or a easier way would be, since see that a easier way would be if I've taken y equal to minus b to b rho dy, and see that this here, the function here is a even function. This is an even function, x square also a y square. So what do we take 2 out and we take 0 to a x square plus y square dx. Okay, so solving we get I is equal to 2 times rho minus b to b dy, and this would be x cube upon 3 plus y square x 0 to a. So we get 2 rho minus b to b dy and if we put this a, we have a cube upon 3 plus ay square. Okay, again we see that here the function is even function. So again taking 2 out, using the properties of definite integrals, it would be 4 times rho 0 to b, and this is a cube upon 3 plus ay square dy, or this is 4 times rho, this would be a cube y upon 3 plus a square a y cube upon 3 from 0 to b 4 times. For rho I will write it here only. For rho we write m upon 4ab, and for this we have a cube b plus ab cube upon 3. Okay, and this is equal to, see 4 cancels out, and if we take the common a b, then we have m upon 3 a square plus b square. This would be from center of, from this z axis, and this can be written as iox plus ioy. As we have calculated in the previous case, iox is ma square upon 3 plus, and ioy is mb square upon 3. So this is only nothing but this is equal to ioz, and this is only the perpendicular axis theorem also, that ioz is equal to iox and ioy if passing to 3 fixed point from passing to center of mass of the body. So we calculated this in this way also, so you can do it anyway. Okay, but if in an examination it is asking the 10 marker question, please don't use the perpendicular axis theorem. Please do by this traditional way. Okay, so now in the next time I'll show you to how to prove conicoid, cylinder, triangle, cone, moment of inertia of cone, solid cone, spherical hollow sphere, okay, and solid sphere, a solid cone, and hollow cone, cylinder. So everything I'll teach you to calculate, how to calculate moment of inertia of each body, and some of the difficult cases also, and also the concept of equipotential, equimomental surfaces or objects, and equipotential this ellipse, momental ellipsoid. Okay, so I'll teach you all those things. For now, you should have the clear understanding of this concept. Thank you.